Hi. Well, basically, I'm not a researcher man, actually. I'm more a practical guy. And there was two previous brilliant talks about the kind of a frontier in the research of the neural network and deep learning. And my talk was, my talk will be full of practical hacks and practical considerations. And first of all, I'm from the computer vision department at Yandex, and we're striving to solve many computer vision problems that are necessary for all. Sorry, where is my presentation? Sorry. So basically, we're trying to solve many computer vision problems that are necessary for all services across Yandex. As well, along with this, we're trying to improve our basic technologies for image and video analysis. Maybe you need a PowerPoint version, or? Oh. Could you go to the first slide? Because this is not the first one. Oh, thank you. Oh, yeah. So today I would like to talk about the approach to obtaining image features that will be suitable for many different target tasks that we face in Yandex. So first of all, I would like to briefly talk about main image analysis problem that we face. And it is certainly the similar images search. So we have a service which you can query with, for example, a photo of a basketball player and get a lot of semantically similar images as on this slide. To solve this task, we need to extract features from the image that, on one hand, will allow us to find semantically relevant answers to an extremely wide range of user input photos. And on the other hand, will make it possible to distinguish between quite similar visual objects, for example, different types of plants. Within the similar images search, we also provide the user with so-called image tags. As you can see on this slide, again, we should work well on many different domains while trying to assign very specific tags rather than just generalized image classes. So, for example, on the left query, we were able to identify the exact printer model based on the input image. And now we're actively trying to solve a localization problem. As you all know, this task is much more complicated than just an image classification. However, the solution of this problem will allow us to better form the search result for the user queries. So, for example, when the user sends an image like this to our search engine, what kind of images he would like to see in response, or more specifically, what is his intent? Whether it will want to look at images of Elon Musk, or maybe it wants to get an images of a Tesla car. We don't know. So this was some kind of problems that we face. And now I would like to discuss what kind of difficulties we can get in the production when trying to solve this task at large scale. First problem that immediately pops up is a problem of small data sets. It is very usual that some internal customer comes to us and with a need to make a classifier of some kind of specific classifier. And at the same time has at best several thousand images as a training for this classifier. Of course, it is almost impossible to train from scratch a large convolutional neural network on such a small data set because of the overfitting effect. So we must be able to somehow solve such tasks with appropriate quality, avoiding overfitting. The second problem is the number of images that need to be processed by our networks in the production. There are tens of billions of images in our search index. And this means that with every update of our algorithms, we must process all these images within a reasonable period of time. Moreover, we crawl hundreds of millions of new images every day, and it is important to quickly add them to the index along with the results of our algorithms. Actually, both problems that I mentioned have one common solution, which is well known across professional community. This approach is called transfer learning. At the first stage, on the left, we train our main large convolutional network on some very large data set of images, for example, an ImageNet. And we expect that the features of one of the last layers, for example, this green layer on the top, will contain all necessary semantic information about an arbitrary image. And after that, we use the outputs of this layer to train on top of them many classifiers on all our target tasks. Basically, we freeze layers below this one and do not fine-tune them during training of our target classifiers. So due to a sharp reduction in the complexity of the model, this allows us to avoid overfitting in most of the cases. In addition, and it is very important for our tasks, we do not need to run separate convolutional networks for each task, but can use a set of convolutions that are common for all of these networks. Using this technology, we can considerably reduce time that is needed to process each image in the index. In this approach, the quality of our basic model, this green width, becomes critically important. This quality is heavily dependent on a original training data set. So the initial data set on which we, like many others actually, trained the base model for was ImageNet with 1,000 of different classes. There are many problems with this data set. First, 1,000 classes are far not enough. There is a lot more objects in the world. And secondly, ImageNet is extremely biased towards wildlife. It is quite fine-graded when we speak about, for example, different animal species, but it is quite sparse and too general for, in other domains, for example, in the domain of electronics. It turns out that the content of this data set does not correspond to the main user topics that users want to search in our search engine. So the first problem we can solve if we will take not a small ImageNet, as in the first example, but the whole ImageNet with entire available WordNet class hierarchy. If we try to carefully select the set of entities, trying to avoid class intersections, we could get a new data set with about 10 million images and divided into about 10,000 classes. This is much better, but still does not solve the bias problem. Some time ago, a new large data set consisting of Flickr user photos was published. This base consists of approximately 60 million images divided into with user tags that are associated with each image. So, however, it is impossible to use these tags as classes without preprocessing because there are quite a lot of absolutely non-visual tags. For example, camera model. In addition, there are many synonymous tags or even identical tags, but in different spelling. If you apply some methods for aggregating and filtering these tags, we could get data set with from 1,000 to 10,000 classes, depending on chosen method. This is also not enough for our tasks. We would like to have an order of magnitude more classes in our data set. So we can try to apply a somewhat different approach to the selection of classes from the same Flickr data set. Photosynthesis data set also have some descriptions. We can consider all the individual words in the descriptions to be in some sense multiple images classes. Of course, first we need to tokenize this text, remove the most frequent words, and then take, for example, 100,000 most frequent words and interpret them as labels. So, for example, this image on the left gonna have labels veranda, hotel, party, and Palma. So, okay, this is fine, but what might be wrong with direct selection of classes from words in the text? First, it would lead to a large amount of noisy labels. Again, there's a lot of synonymous words that are difficult to merge automatically. Also, in the description of images, there may be words that are either do not directly related to the image itself, or are difficult to predict based on solely image content. Such noise in the training data will greatly complicate the optimization problem. Secondly, we'll have to somehow limit the number of words that we take as classes. In the simple case, we can just cut our vocabulary based on some kind of a frequency threshold. But it is likely that many of the concepts that we are interested in will be below this frequency concepts, this frequency threshold, sorry. We can try to select a set of concepts of interest in a smarter way. For example, choose only nouns or words that denote some kind of object. But in any way, this approach will require a lot of manual work. And, well, the third problem that we will face is complex concepts. So this is a concept that are either difficult to express in one word or that are described by multi-word idiom. A very good example is the chocolate factory Red October, actually, which is near us. Or some movie caption, because neither of the separate words describe the concept, the whole concept. So are there any other ways to determine the set of classes? A very important aspect that I would like to point out, that for vast majority of our target tasks, we do not need named or in general human interpretable labels, because we want to use these models only as a proxy for other tasks. Let's consider the case in which there is corresponding text to every image, like in a Flickr dataset. We could use some method to take all of these descriptions and cluster them into a fixed number of clusters. Then we might use resulting clusters as classes of entities. In the case of Yandex, users query our search engine with tens of millions unique queries per day and then click on some images on the resulting page. And we could consider these queries to be in some sense descriptions for clicked images. Ideally, we would like to have clusters like this. In these clusters we can separate, for example, very far away classes like horse and mobile phone, but ideally we would like to separate even photos of horse and drowning of horse, because this is a very different visual concepts. Obviously, first approach to clustering user queries is to transform it into some kind of high-dimensional vector space using some kind of distributed embeddings for words like word-to-work or glove. To obtain representation for a query, we just sum up individual representations of each word in the query. This is a very common practice. Then we could use, for example, k-means algorithm to cluster these embeddings. This slide shows a fairly typical example of the resulting cluster. Sorry, this is in Russian, but I mean, it's hard to translate all of these queries in English. So one can see that in general, we get quite similar queries in this cluster, yeah? So this is images of some animals. However, in this case, syntactic similarities affects the results much more than semantic ones. We can see queries about tiger, about an elephant, and about a frog, and much more. We would like to have more fine-graded classes. So at least it turned out that the clustering approach somehow works. It remains to understand how we can get better representation for queries. And we again decided to somehow utilize click data. After a user sends query to the search engine, he might click on the different images. Users click more on some images and less on the others. On average, this may indicate the degree of relevance between an image and a query. We can take the entire click history, and for each pair of request and image, calculate the so-called CTRs, So CTR is basically the ratio between number of clicks on this image and number of times that this image was shown in response to a particular query. For example, on this slide, we use as an example a query racehorse, and there's a free corresponding images, and this is a CTR. So we can see that, for example, the drowning of a horse is clicked much less than, for example, a photo of a racehorse. So basically, then we can calculate for each of this image features from one of our previous neural networks, from one of our previous models. And then we can get the embedding of a query, but just a weighted summation of these features taking into account corresponding CTRs. Yeah? And this is how we basically get an embedding for a text based on an image representation of this text. It is important to understand that in order to obtain a more reliable representations for queries, we need at least some minimal click history for it. Therefore, we had to discard all requests that was asked less than a certain number of times. So again, one of the clusters using these images features embeddings are shown on this slide. This is a cluster about Maine Coon cat breed. Yep. So we're able to merge into this cluster many different spellings, including grammatically incorrect. However, if we had a look for the closest cluster to this one, then we will find a virtually identical cluster filled with the same Maine Coon queries, but in a slightly different formulations. We would certainly like that all these requests fall into the same cluster. Then the network would not have to try to distinguish these two visually identical classes. So, after more detailed study of the structure of the resulting clusters, it turned out that this is not an unusual case, actually. This is a frequent problem. If we plot the distribution of intercluster and intercluster distances, we get the graph like this. And we can see that first, these two t-distributions are heavily intersected. And second, it turns out that the average intercluster distance, so that means the average distance between points that belong to this cluster, to the centroid, is even smaller than is even larger than the distance between two nearest centroids. So it is possible that this is some kind of artifact of the linear k-means algorithm that we're using for clustering. However, we decided that we can take the resulting cluster and try to merge the most similar ones. There are many ways actually to determine which cluster we would like to merge, but we use the following approach. We have tried to merge clusters with large amount of points that are placed near the cluster boundaries. So, for example, these points belong to one of the cluster. Sorry, do I have? Yep. Oh, okay. So, for example, on image on the right, there are some points that belong to one of these two clusters, but the difference between the distances to the next nearest centroid does not exceed a very little amount. For example, 100. So the distribution of distances to the nearest centroids is shown on the left. We removed from consideration object with distances to the nearest clusters that exceed this red line. We did it because we actually interested in merging small clusters in a very dense region of space, and these points are not interested for us. So basically, as a result, we utilize the following approach. For example, we would like to get 100,000 clusters in final. To do this, we can initially cluster the space into, let's say, 150,000 classes. And then sequentially merge the clusters with the largest number of these shared boundary points. So far, we have automatically select a set of 100,000 classes. To fill these classes with images, we gonna take images that were shown and clicked by user in response to some query. Sometimes it turned out that there are too few images, and then we just threw away this cluster. Sometimes, in contrast, there are too many such images in some of the clusters, and then we just took a fixed number of them with the largest CTRs. Quite often, one image falls into several clusters. In such a situation, we assigned it to a cluster in which it had the largest CTR. As a result, we obtained distribution of cluster sizes that is shown on the slide, with the median size of the cluster is about 600 images. So, well, okay, let's move on to the real results. So as a baseline, I would like to show you the error that we obtained after training on this data set, for example, for ResNet 50. Well, it's slightly above 80%. And it might seem that this is kind of a very bad classification error, right? But remember that we are not interested in this classification error. We are interested in our target classification errors on target tasks. And so on this slide, I present comparison between our previous basic data set, ImageNet 10K, and one that I described today. Basically, there are several classifiers that was trained on top of features from two different base networks. As you can see, in the case of relatively complex classifiers, such as clothing, for example, we have obtained a very significant growth in the accuracy metric. However, in the case of some simple classifiers, like, for example, a porn classifier, we didn't observe any growth. This is all certainly interesting, but all these classifiers are quite specific. And our task was to significantly improve the quality of our algorithms on a very wide range of user topics simultaneously. To check whether we really improve our base neural network or not, we could have a look at the aggregated metric for quality of similar images search. This is a very simple metric. We have a limited number of images as queries, and then we use an assessors, people who estimate how relevant our search result in response to these queries. According to this metric, when we switch to, oh, sorry, wait. There should be next slide. Yep, sorry. Yeah, so according to this metric, when we switched from our previous data set to this one, to clusters data set, we got an increase in 10%, which, to be honest, was a great leap for us. We went a bit further and tried to train the network simultaneously on these two data sets. It doesn't work? Okay, thanks. And surprise, surprise, we got another 10% improvement. In general, this means that the cluster's database is still not a superset of ImageNet. And it is beneficial to use both of them for training. Okay, and the last slide, so with the take-home points, and I will briefly run through it. So first of all, it's quite obvious for all professionals that transfer learning is a way to quickly train models on a small data sets without overfitting. Secondly, we can dramatically reduce computation time for a single image by sharing heavy convolutional layers for many tasks. I think that at least I was trying to convince you that we do not need named entities in our data set to train a base neural network model. And, well, the more classless entities, the better its final quality. So, thank you very much.
Okay, thanks, Konstantin. You have any questions?
How do you publish on your large data set?
Whoa, I expect this question. Are we going to publish this data set? I don't know. Actually, I don't have an answer for this question because this is our internal data set, and, well, at least for now, we do not have plans to recently publish it.
Other questions?
So, if I'm to understand correctly, you're representing your images in the feature space where the words describing the images are features, right? And the clickability as a distance from the mean or from the word that describes, right? So how would you counter that some images by their own nature is like more clickable, like if you're searching for some image and you see the other image that is not described by this word you input in the search query, but is more interesting for average person. You know, how would you counter this kind of mistake during the search?
Well, basically, I'm not sure that I fully understand this question, but I will try to answer.
I could rephrase in Russian if you like.
Sorry?
I could repeat it in Russian if you like.
Yeah, if it's possible, because.
Вы представляете изображения как объекты в пространстве вот этом семантическом, ну то есть в пространстве слов, грубо говоря, где вот слова как признаки. Но вот некоторые изображения могут быть более интересны пользователю просто в своей природе, хотя они связаны с вот словом, которое он вбивал в запрос. То есть, это известная проблема. Вы ищете что-то по каким-то словам, а вдруг видите что-то интересное. Вот некоторые изображения просто в принципе более интересны. Как вы такую ошибку устраняете?
Well, the question is basically about what we do. So there's a very frequent situation, for example, when a user makes a query and then see a result page with several images, and then there are, of course, images that are relevant to this query, and then suddenly there is images that are not relevant to this query, but in some sense more interesting or more attractive to the user, and then the user clicks on this image, and this is kind of a noise in our click data. Yeah, for sure, we always face this problem because click data is very noisy, and moreover, actually, this CTR's level is heavily dependent on the type of the queries. Because, for example, on some queries, user do not click on any image. So the problem of user is solving just by looking at the result page. And for some queries, user usually clicks on some images to see it in a full size. Yeah, so we are trying to apply some kind of filtering method. So, for example, filtering a normal values of the CTRs, for example, too high or too low, or maybe that are not in the free sigma, for example, from the mean value. So some kind of these methods.
Okay, one more short question.
Вы показывали слайд, где и говорили о том, что вам не нужно строго формализовать метки, формализовать аннотации, достаточно их классифицировать. Вы можете, там, где вот у вас красным, розовым кружочком, овалами были, да, метод классификации такой, можете подробнее объяснить?
Okay, so basically, most of the time, the open data sets consist of images that are labeled with named entity. Yeah, so we can associate with each image some named label. And our approach is to try to go a little bit further. So basically, we do not need these named labels. We just need a set of texts that somehow represent the concepts. So we don't need to merge this set of texts into one word. We just need to have a representative text from the cluster. And this is how we actually found this set of concepts.
Okay, let's thank Konstantin again.
Thank you.